Hey everyone, thanks for joining us today. My name is Namdi Regmulam. I'm a partner at Lightspeed Venture Partners. And today I have with me Andy Zhou. Andy is an incredible AI researcher who, in a relatively short period of time, has made some, really strong contributions. Andy is currently a graduate student at the University of Illinois, UIUC. He also actually recently joined Meta, working as a researcher on various AI related topics. And, if that wasn't enough, he's also co-founder and head of a research lab called Lapis Labs, which is a student-led research group. And, despite the kind of relative youth of some of its members, they've already kind of published in some top tier venues. And so Andy is no slouch. I really appreciate him joining us. Welcome, Andy.
Yeah, thanks for the introduction, Namdi.
Yeah, of course. Maybe it would be helpful before we jump into some of your papers and research agenda. I think it would be helpful just to maybe get, your story, how you got into AI in the first place.
Yeah, so I got into AI a little bit around 2022, I would say. I was currently an undergraduate at UIUC, and I was just pretty interested in AI and its potential applications. So this was before LLMs were popular, and this was before ChatGPT was out. So there was a lot of more uncertainty about where the field was headed and what it could become. But I was always pretty passionate about the idea of AI that can do human level tasks in a general manner and could potentially surpass humans in some domains. So that was always the goal for me to do research. And I started just joining some labs in my school. I started working mostly in computer vision. And then once LLMs became popular, I kind of saw that this was where things were headed. And I mostly focused on one, improving the capabilities of LLMs in agentic applications, and also identifying some of the vulnerabilities that these systems have and creating methods to patch that.
Very cool. And if I remember correctly, when you and I met originally last year, I think it was around that language agent tree search paper, and which I thought was really interesting, which is why I reached out to you initially. I thought this was a really interesting, piece of work, and it would be great if maybe you could start with, the full name of the paper is Language Agent Tree Search Unifies Reasoning, Acting, and Planning in Language Models. And so I thought it'd be a great place to start with just the kind of spark behind that idea to unify all those things in a single framework. Like, where did this kind of come from, and yeah, how did you land on this?
Yeah, sure. Yeah, so language and tree search or LATs. At a high level, essentially, we're applying Monte Carlo Tree Search to LM agents as a general way to improve their capabilities. The idea here is that we're trying to add planning and backtracking agents. So instead of only sampling one action at every step, it's just better for an agent to explore its environment and try many actions at every step. And then after it's done this, construct an optimal trajectory out of what it explored. So the idea behind unifying reasoning, acting, and planning is that essentially there's around this time we did this work in 2023, and this was after GPT-4 came out, and there were a few directions that were pretty relevant here. The more popular one was just reasoning. So this was before reasoning models. So LLMs were pretty limited in this domain. And
Hmm.
the best performance people got was just trying chain of thought prompting.
Right.
Whereas the idea behind chain of thought prompting is that so instead of just doing a left to right decoding with the next token, where it's intuitively pretty hard for an LLM to just know the exact final answer, we can instead do have it generate a reasoning trace, and then the correct token answer is more likely to come out of that reasoning trace instead of just giving it the question directly. And yeah, the problem with just doing chain of thought prompting is that it's still reflexive in the sense that instead of just token by token, now it's just kind of reasoning step by reasoning step. So if we think about how humans tackle math problems, instead of just doing every individual step in one go, humans will tend to tackle problems in a way where we can plan ahead, backtrack the previous steps if there's errors, and consider multiple potential reasoning steps at every step. So things like search algorithms, which were popular in reinforcement learning, were adopted here with LLMs. Paper was called Tree of Thoughts was the first to do this. And they basically, yeah, injected planning into a reasoning for LLMs. And then concurrently to this, there was also a lot of interest in LLM agents and how to deploy LLMs in applications where they would navigate the real world and perform tasks there, such as using tools, doing agentic tasks. So for agentic tasks, it was pretty similar to reasoning tasks in a sense where standard LLMs couldn't do very much. And the setting is also challenging in other senses. And like, for example, trajectories are typically a lot longer. So there's a greater chance for if an individual step at the beginning, if there's an error there, it could propagate to later steps and have a greater impact. There was also a lot of challenges in getting agents to work. So for our labs paper, yeah, the idea was that we wanted to kind of combine these two trajectories of reasoning, planning, and agents into a unified framework where every individual subdomain can help the other ones and create a more general framework where an LM agent can solve tasks by doing reasoning and planning.
Yeah. It's interesting, right? It's sort of like prior to the sort of chain of thought, chain of research, no pun intended, the idea was sort of like, hey, we need to get these models to basically produce the right answer, immediately. The next token had to be, the right token effectively. Versus with, chain of thought and some of these other things, as you said, sort of with additional tokens, there's sort of more opportunities to, get to the right answer. Now, normally the critique for these autoregressive models is, oh, the errors compound over time, as you kind of alluded to, and so you might not think that that would work. But what you're kind of saying is, well, we can prevent the errors from compounding by allowing the model to backtrack and do these other things within that sequence, within that trajectory, and so still end up with the right answer by the end. Is that effectively right?
Right, right.
Yeah. And so you kind of took the almost like the space of different almost like operations that one can do as you're sort of navigating this search space, and you kind of broke it down into these 6 different operations. So there was selection, expansion, evaluation, simulation, back propagation, and reflection. I thought it'd be interesting maybe to just like it'd be great to just like walk through these and maybe talk a bit about how did you even come to these 6, like why is this kind of like the right set to be working with?
Yeah, of course. Yeah, so I guess the end goal of LATS is to basically construct a tree. Like you can see this figure where every node in the tree is like a state in the environment, and every state will have things like the action and the observation the agent gets. And then once this tree is constructed, every node is valued. So you can just directly construct the best trajectory from every level by taking the highest valued node, and that will be the best trajectory instead of just, yeah, sampling only one node at every step. So the 6 steps of LATS is the way to basically construct this tree and score all these nodes. Most of these steps are taken directly from traditional Monte Carlo Tree Search, which has been popularized in things like AlphaGo and reinforcement learning. And we also took the liberty of adapting some of these steps to the LLM setting and also adapting some LLM specific techniques to Monte Carlo Tree Search. So the first step is called selection here. So this is basically where we just select the state to continue from. We use a technique called UCB, which is basically a way to balance always picking the node with the highest value with exploring nodes that haven't been visited as much, since we want the agent to basically go to points where it hasn't explored as much, where it could potentially have a higher reward. And the second step is called expansion, where after we select the state, we basically have the agent sample several actions to propose things like what we'll try to do next. And then after this is done, in the third step, we label each of these new actions with a value based on how likely it is to lead to a positive final outcome. And the cool thing here is that we actually use an LLM to assign this value instead of training a value function. And then for the fourth step, we basically continue the previous 3 steps until we reach a final terminal node. This is like the final outcome where we know if the agent has either succeeded or failed. So for example, if we're trying to get an agent to navigate the web and buy something for a user, this is where it's finally decided which item to purchase, and we can know if it was the right item or not. And then for the fifth step, after we get this final outcome, essentially a very useful signal, and we could update the values of the nodes that led up to it based on if the agent succeeded or failed. And then for the final step, this is the step that's unique to LLMs, is we use a technique called self-reflection, where we have the LLM summarize its own trajectory and errors, and the summary is used in the future so that it's less likely to make those same mistakes. Yeah, and then those steps lead up to a final tree where we have nodes at every level that are labeled, and we can just take the the node of the highest value at every level, and that becomes the best trajectory that we can use for the final task.
Great. And you talked about how, in some sense, what you're doing here is, adapting, Monte Carlo tree search to the language modeling context. I'm curious, like, what sort of adaptations were necessary to do that? What sort of challenges did you run into as you were trying to kind of construct this?
Yeah, so the main thing is we wanted to keep it simple and easy to use for protection for like users. So this meant that we wanted to stick with only pre-trained models and not have to train any additional modules on top of that. So for additional like Monte Carlo tree search for the value function, it would need to be trained. So
Yeah.
instead of doing that, we just use a pre-trained LLM and had to essentially act like a verifier or a judge and score each node based on whether if it was gonna be successful or not. And this was actually better to do in the agentic setting than just a pure reasoning setting because we found that by giving this value function, this LM value function, the observation for the environment, the observation was actually a very good signal that could kind of intuitively tell it whether or not the node was going to be successful.
And could you, just for the sake of folks, because I think for a lot of people, they kind of synonymize reasoning and agents and whatnot. So maybe separate those two for the audience.
Oh yeah, so for the purpose of this paper, reasoning is essentially an LLM just doing a task without any input from the environment, and an agent will be doing a task and it would have an external environment like APIs or tools that it's getting feedback from.
Got it. Okay. Yeah, that makes sense. And one of the questions I always have with, someone puts out a paper with a particular technique, it performs well on certain benchmarks, what have you. The question is always a little bit like, what are the trade-offs here? Like, where is this kind of approach, most useful? What are the edge cases that maybe it doesn't handle as well? I'm curious if that was something, you were able to explore as you were working on this.
Yeah, so we did explore this a lot. So the main, I guess, drawback for now is the inference cost. So you can imagine just doing search and sampling and trying having agent explore would cost a lot more LM calls. And we found that in our environments, it usually took around 10 times as many LM calls as just doing a standard like chain of thought trajectory. But then the good thing is that when we did this in 2023, it costed around like $5 just to do a human eval programming question for this agent. But then costs have gone down significantly, and now it would only cost a few cents, even when using this ELATS approach. So I would say that it's pretty good for situations where people could care more about performance than cost, such as very difficult reasoning problems. And also, LATS is designed to be customizable. So the users can essentially decide how many nodes they want to sample at every step. And if, for example, only one node is sampled at every step, it kind of just reduces down to chain of thought prompting or React prompting. So that's a way to kind of get around these drawbacks and trade-offs.
And you mentioned that this method is, I think you said 10x more expensive than kind of vanilla chain of thought. This kind of firmly places it within this kind of emerging paradigm of test time scaling where, you know, it's sort of up to either the user or whoever's controlling the model to kind of set how much compute it wants to use, at inference time to answer questions. The idea being you can use more compute to get better answers, and you can at least explore that trade-off between, cost and quality. Is that right?
Yeah, that's right. Yeah, so for reasoning models, one drawback is that it's kind of able to decide how much compute it wants to use, but then the user can't determine how much compute. For this one, it is more configurable in the sense that there's more hyperparameters the user can set in how many times they want to sample and how long the search can continue for.
Yeah, and so you were, in some sense, early to some of this test time scaling stuff. I mean, now it's like everybody wants to talk about it, and I want to talk about it, but you kind of were early to this. I'm curious, like, given you were a little bit ahead of the game, what was surprising to you at the time? Like, what about these results were like most interesting or most surprising, or what kind of shocked you as you kind of went through this research process?
Yeah, I think when we just started, I didn't really have any clear idea of how where it was going to go or if it was going to work. And I guess the main surprise was just how good a generic LLM that hasn't been like improved very much is at these tasks that are required difficult reasoning or acting. We found that like most of the time an agent or LLM agent is able to do it pretty well. it's able to perform individual steps correctly eventually. It's just very hard for it to get the correct action or reasoning step at every time in like a single go to finish the task. So I guess it really showed like the potential of LLMs eventually becoming what where they are today. And it does show like there's also more potential for it to become even better and get better at these agentic tasks.
And when you say that you were surprised by the performance of like a baseline LLM, you're saying an LLM that hasn't been fine tuned on these trajectories.
Right. Just like vanilla GPT-4, we
Yeah.
found that for some domains, using the search-based approach was able to double its performance when just doing change of file prompting didn't work as well.
Yeah. And there's all these sorts of interesting ideas about, what that implies about the kind of inbuilt capabilities of the base LLMs that they kind of acquire during pre-training, and what it is we're really doing when we maybe later either prompt or fine tune these models. Is it sort of like eliciting latent capabilities that were already there? Is it actually putting in new capabilities? It's an interesting question. And I feel like, in the time since you published this, probably one of the biggest pieces of news is, in addition to reasoning models in general, this DeepSeek R1 in particular, which really, has sort of caught the imagination of the world, it really seems like, and changed how people think about these models. I'm curious, like, you're kind of alluding to this, but what are your kind of evolving thoughts on, LLM reasoning and test time scaling, et cetera, in the advent of R1?
Yeah, I think R1 and O1 really showed kind of like made it to a point where like similar to like ChatGPT and with LLMs, it shows that reasoning models are kind of probably going to be the next big thing in AI. Yeah, like you said, for LLMs, they already have been trained on the entire internet, which is a lot more tokens than any human has ever witnessed in their lives. So they do have like superhuman like latent knowledge. It just wasn't really extracted properly with the standard training techniques we had back in the day. So now with reasoning models, the models have been trained to actually leverage this knowledge and use it in a way to perform difficult tasks in programming and math. And there's a good possibility that with the way RL is structured, where there is just like a verifiable reward and no human input, it could eventually learn to reason beyond a human level. And I'm pretty excited to see where that takes models and what applications that enables.
Yeah, I remember at NeurIPS a few weeks ago, I had two big questions that I asked basically everyone that I spent time with. One was, on balance, do you feel like test time compute and these different methods that are emerging, on balance, favor the big AI models versus big AI labs versus everybody else kind of working in this ecosystem, et cetera? And then two, there will probably be areas where this kind of capability is more useful than others or more capable than others or what have you, like certain areas where being able to explore that trade-off between performance and cost is more interesting. There's gonna be certain areas where you just want the best performing thing, basically at any cost, and there can be other areas where you're like, no, I'd prefer to have that knob to be able to dial in. And so I got a lot of interesting responses. I won't regale everybody here with all that I heard, but I'm curious, any thoughts on those two questions?
Yeah, I think with the release of DeepSeek R1, it does kind of democratize at least both access to the best models, and also it shows that it's a lot cheaper than people expected to actually train models of this level of capability. And there has already been several works that they don't do the full RL pipeline, but they show that creating just some samples from these powerful models and training a weaker model on them for like distillation is able to recapture a lot of the high reasoning performance that the initial model had. So it's pretty exciting for research in general here to kind of explore like to what extent these capabilities can be distilled and how cheap the models can actually be eventually down the line.
Yeah,
Yeah.
I'm personally quite bullish about you know the demand for these capabilities as it gets cheaper. My sense is that I study economics in school, and my sense is that like the demand for this stuff is very elastic. As the price goes down, I think the demand for it will increase pretty dramatically. And so I think all these developments are just super exciting, and I'm very curious to see where we end up in the next few years. Maybe we can also now switch over to talking about your other paper. The title is AutoRed Teamer, an autonomous red teaming agent against large language models, which kind of tells you exactly what it is. But it'd be helpful if maybe you could give some of the high level color on some of the ideas here, what you were trying to accomplish, and what you did accomplish.
Gosh, great. Yeah, so this is a paper that was the latest paper I worked on and will be released pretty soon. So this is something I did as a research intern over the summer at Virtue AI, which is a company that does red teaming as a service. And the idea of this paper is it's a bit different than the previous one, but it's still tackling LLMs and LLM agents related topics. So the motivation is like all systems, AI-based systems have vulnerabilities, security vulnerabilities that attackers can exploit and cause economic damage. And for LLMs, the main vulnerability that people have studied is called jailbreaking, where the idea is that people can create prompts that would cause the model to refuse like a request that would normally cause it to like answer a request it would normally refuse. So everyone probably has like tried getting ChatGPT to say bad words and seen that it doesn't do it. And there's ways to like trick it that it will do that. And right now it doesn't have like too much intrinsic value because it doesn't really cause any like damage for ChatGPT to say bad words. But we can imagine like scenarios in the future where an agent that is autonomous can be jailbroken to like reveal users' credit card information, and that would be pretty bad. So you want to kind of get ahead of these vulnerabilities early and study them while before they're at the point where they can cause real damage. So the goal of this paper is a work in this domain where we want to do something called red teaming, which is trying to systematically discover these security vulnerabilities of a target system before releasing it. And traditionally, red teaming has been done just with humans. So we have it's been done like at OpenAI and Anthropic, where they have teams of human red teamers that are experts in their domain, essentially like sit down and try to get these models to do the things they shouldn't do and manually try to identify all the input prompts that can cause bad behavior. But this has some limitations in the sense that eventually it just doesn't scale as well and also, there's a very high possibility for human red teamers to miss certain areas or prompts that are so out there, but they haven't found in their red teaming process. So to get around that, we're trying to do something called automated red teaming, where instead of using manual human red teamers, we're instead using an LM agent itself to do this red teaming process systematically and autonomously, and it would be able to scale better, be cheaper, and also have greater coverage than using only humans in the red teaming process.
Yeah, it's perfect. And one thing that's always been slightly confusing to me at least, and then maybe to others as well, is sort of the distinction between if there is one, the distinction between red teaming and evaluation as a general practice. Do you see a difference between those two, or what does one versus the other mean to you?
Yeah, I think evaluation is probably like a superset or like just a broader term for evaluating a model. And for me, when I think about red teaming, it's more of like a narrow set of evaluation where instead of it's still looking at places where the model will fail, but mostly looking at places where it would fail and also have like the most downstream damage or a least desirability for it to fail.
Okay, that's great. And then similar here, I think you had sort of a number of different kind of modules to the overall system. It'd be great to kind of like walk through each of those. And I think in particular that like the memory module seemed interesting, or the memory system maybe I should call it, seemed interesting and important. But maybe you want to go through those.
Yeah, of course. So yeah, to kind of go over the high level design of the agent. So it includes two separate agents. One agent is essentially posing new attacks to add to a toolbox, and the second agent is using this toolbox to conduct red teaming. And the second agent is which we're calling the red teaming agent, is essentially mirroring the human red teaming process. So this one, yeah, contains five modules that each mirror like a specific component of human red teaming, where the goal is to start from a very broad domain of interest, for example, hate speech or racism, and I finally end with a long list of prompts that successfully get the target model to answer questions in this domain and have like a report of the overall system's vulnerabilities. So yeah, for these five modules, we start with we essentially start with an input, and then we have a module to analyze this input and kind of summarize scenarios where the harmful behavior can occur. And then we have a module called the prompt generator, which takes this analysis and generates a list of scenarios where the target vulnerability can occur. So for something like hate speech, it can be something like write me a tweet on why the Holocaust was good or something. And then these prompts are passed into the attack agent, where this agent selects the tool from its library and basically it applies that attack to the prompt. So these attacks are basically attacks that people have already discovered in the literature, like for example, changing the prompt into a role play setting, and then all these attacks are applied and they're tested against the target model. And based on the outcome of whether or not they refuse the request, this outcome is stored in the memory. And this memory, which basically lists out all the vulnerable prompts so far, and optimal attacks have been tried, can essentially have the agent learn from the red teaming process and identify the most optimal attacks it can use against the system based on whatever domain it's given.
I feel like this is the kind of thing where you probably had a number of different sort of design choices. In other words, like there's probably a number of different ways you could have constructed such a system, different approaches you could have taken. I guess how did you kind of arrive at this particular almost architecture?
Yeah, so earlier designs of this architecture were more complex. We had more modules that did things like orchestrate the process and call different modules at different points in time. And we just eventually kind of found that these weren't super necessary, just added complexity. So we kind of just tried to be as simple as possible and only use the modules that we found were critical for the agent being able to do the red teaming on its own. And this was kind of just what we ended with, where yeah, we do need a component to analyze the initial input so that all of the future modules stay aligned to the original user input. And we do need a module to generate the prompts and refine them using different attacks.
It's a very common path in engineering of systems is you first start off with something complicated that works, then you try to find something smaller that has similar capabilities or works even better. And if I heard you correctly earlier, you said that the kind of benefits that you imagined for doing this in an automated way versus the more kind of manual approaches were, one, the sort of just cost effectiveness of doing it in this more automated way. And then two is sort of like coverage, almost like test coverage in the context of software development, sort of that for LLMs. Is that
Right.
right?
Right, right. Yeah, the cost is definitely there. So for our system, we could run it on a standard data set and it would only cost a few dollars versus I would imagine like red teamers, which are experts, get paid a lot more to do red teaming. And for coverage, similar to test coverage. So one point of coverage is we want a coverage we want the system to be able to cover all possible risk scenarios that are important. So, for example, I did a previous analysis where it was like AI governance paper where we looked at AI policies like the EU AI Act and found that in all these policies there were 314 different risk categories like hate speech or CSAM that people find important. But most existing red teaming data sets and things like the categories that OpenAI releases only cover a few of these. And so there's a need for greater coverage in order to even like maintain compliance to some of these policies. And the other point of coverage is we want to maximize the attack coverage. So a lot of existing jailbreaking attacks only consider singular attack vectors. So for example, they only find like existing one way to attack the model like roleplay and don't consider how roleplay will interact with other types of attacks. So we want the system to be able to essentially kind of create optimal combinations of all these attacks, which is what like real adversary would probably do instead of only trying individual attacks.
Yeah, it makes sense. I was at a conference a few months back called The Curve, and it is really, really interesting. There was one talk that I attended that was on, AI security. And, the point was made, which I think is a good one, that, defense in the context of security is very hard because the attackers only need to find one way in, whereas the defender needs to defend against every way. And, in some sense, you're leveraging that, very deep insight to construct this, where they're saying, hey, we should be trying every way in and in combination and different sequences and what have you. in order to fully sort of like robustify the underlying models. So yeah, that makes perfect sense. And then I'm curious, like, what kind of almost insights did you sort of come to about LLM security as part of doing this work, and maybe some of the vulnerabilities you were able to find, etc.
Yeah, I think the biggest insight was, yeah, what like you said, it's combinations of attacks work a lot better than individual ones. And certain attacks can be generally applied to other attacks to kind of boost their success rate kind of almost universally. One of these attacks was this the attack called few shot, where essentially people create few shot examples of models responding to harmful requests. And like similar to like real few shot examples, they can kind of just be applied pretty universally. And
Mm-hmm.
we found that applying this attack to other attacks could boost the attack's overall success rate. And another insight was, or at least the best attack we tried individually was Pliny the Prompter's attack that he released on GitHub. So we could actually just inject like human written prompts as well into the toolbox, and the agent can leverage those as well to attack the target system.
Yeah, I mean, you said something very, very interesting, right? I mean, you basically said, in some sense, what we know, which is that, prompting and various forms of prompt engineering are ways to get the model to do what you want it to do more, reliably and consistently. What we want the model to do, if you're a nefarious attacker, could be something, nefarious. And so those same techniques that we use to get the models to do what we want can allow other people to do things to the models that we don't want them to do in
Right.
some sense. And so, not to suggest to any black hat hackers out there, but someone could use your language agent tree search method to get a model to do the bad thing. Actually, is that reasonable?
Yeah, there's actually some attacks that use tree search as like a way to search through the attack space and get the model to and find vulnerabilities better.
Yeah, it's sort of the classic cat and mouse game in security, where the attackers find some new thing, the defenders try to defend against it, and the attackers move on to some other new thing. Except in this case, in some sense, a lot of the tools that the good guys are creating, again, to get the models to perform better, can also be used by the bad guys, like those same exact tools. These AI security discussions can get dark very quickly. You're like, I don't know if these things can ever be truly defended, but I'm curious, like, how do you feel about that? Just you, when you've been working in this space, like, is it similar to traditional security, where it's sort of like you can defend against what you know, but there's always sort of unknown unknowns that are hard to defend against? Or do you think we ever get to the point where we can really kind of robustify these models?
Yeah, that's an interesting question. I think for it's definitely different than traditional security in the sense that just LLM or AI-based systems have certain behaviors and they're more black box and less deterministic. So it's a bit harder to actually know all of the ways it can fail. But also with kind of like with what I designed with this system, it's also possible to use AI systems themselves as part of the security process and automate some of these vulnerability discovery techniques and also potentially down the line maybe automate some of the ways to defend against the attacks as well. So that could be like a potential avenue to get around this cat and mouse problem where instead of it's just humans versus adversaries, the AI is also part of the equation here and and can really speed up some of these processes.
Yeah, very cool. And then, one thing I wanted to ask you was, I feel like when it comes to, AI security, there's things that the underlying, if it's a closed source model, for example, or even if it's an open source model, that the original model trainer can do in order to kind of secure the model, prevent it from generating harmful outputs, etc. Anthropic has published a lot of great work around this, various forms of constitutional AI and other things that are generally meant to get the model to stay in the lane that you want it to stay in, as opposed to go off the rails. And so they're gonna, the big AI labs, I think, are gonna continue to do that. I think it's in their best interest to keep doing that, because they don't want to be the face of some bad behaving model of some sort. But they're not going to be perfect. And so as consumers of AI, we receive these models from these large labs, as secure as they are, but not perfectly secure. What can folks who are just consuming these models do, in your opinion, or what should the takeaways for them be as far as how to securely use these models and avoid, some of these issues and vulnerabilities, which will maybe inevitably be there at least in the near term?
Yeah, I would recommend probably just doing enough due diligence and on top of just standard validations of this, how well the system performs, also kind of thinking about it in a security context and seeing like where a potential attacker could be able to exploit the system. So for many applications, yeah, things like this problems we study about just like hate speech and things probably don't apply as well. But depending on the application, with things like users' private information, there are other avenues where it is important to make sure the system is secure. So I would just recommend, yeah, doing enough evaluation of how it could happen. And there's also other things like instead of actually modifying the base model, there's ways to use things like guardrail models where we have external systems and modules that can actually monitor the agent's behavior and ensure it avoids certain things that we don't want it to do.
Yeah, there's a number of companies that we've spent time with that are working on guardrailing technology of various sorts. So it's definitely an interesting avenue. Maybe just to end off here, what are you kind of most excited about? What's on the kind of research agenda to come? What kinds of things should people be on the lookout for?
Yeah, currently I'm pretty interested in agents in general. So I think with reasoning models, the base capabilities of an LLM has really exploded, and I want to see how that translates to better applications and better agents. So if there's a relationship between how well a model reasons and how well it performs in a agentic setting, and also yeah, how to best leverage inference computes methods to improve agentic performance. I think it's yeah, agents are they've always been pretty exciting, but I feel like now is the time where a lot of these applications are at the level where it could be deployed and have a really tangible benefit. That's pretty exciting.
Yeah, very very cool. I've personally come a long way on agents. I think when I first heard the term and I saw what people were referring to as agents, I wasn't as impressed. I'm much more impressed these days, and I'm quite excited about it as well. So, um, thank you so much, Andy. Really appreciate you doing this. This was great. Again, as I mentioned, you've been extremely productive as a relatively young researcher. So I'm actually mostly excited about what you have yet to publish and what is yet to come in your kind of research journey. So, thank you for doing this and congrats again on the new role at Meta.
Yeah, thanks, Namdi. It was great to be here and talk about my research.
Yeah, of course. Thanks everyone for joining us. Really appreciate it. I'll see you for the next one.